So we know it diverges at -1. And I'm going to try to squeeze the rest of it in here. Diverges at x equals -1. Okay. So that means your interval of convergence is equal to -1, 1, but 1 is the only one that gets the bracket. Okay. So we went through all that work to try and figure out whether you use a parentheses or a bracket. All right. So any questions on that one? Oh, a little bit tedious, but overall not horrible. As long as you know your test. If you're kind of rusty on your test, it'll seem horrible. Let's bring that down a little bit. Uh-oh. Okay. Okay, so let's say for our next example, write out the first 4 non-zero terms of the power series representation for f of x equals the natural log of 1 plus e times x by integrating the power series for f prime of x. So you're going to get the derivative, and then you're going to take the integral. Okay, so if we have our f of x equals the natural log of 1 plus e times x, that means our f prime of x is equal to e over 1 plus e times x. Not e to the power of x, e times x. I say that because I wrote e to the power of x over and over and over again. Just out of pure habit. Okay, so we know that f prime of x is equal to the sum. Oh, actually, let me move that over a little bit. The sum from n equals 0 to infinity. We're going to bring that e out to the front. Okay, so that's going to be -1 to the n times e to the x to the nth power. Okay. So if we remember when we had our natural log of x, then when we found the derivative of that, it canceled out the n. So we're right back here. Okay. So we know that's going to equal, if we plug in 0, you have e to the 0, so you have 1, 1, so you have just e. If you plug in 1, you get negative e squared x. Because you have e here, you have e there, you get e squared to the x. Plus e to the third x squared minus e to the fourth x cubed plus so forth and so on and so on. Okay. So now we're going to integrate all those terms because they wanted you to get the derivative and then integrate it. You have the integral of f prime of x with respect to x is equal to the integral of e minus e squared x plus e to the third x squared minus e to the fourth x to the third plus so forth, so on, and so on with respect to x. We'll bring that up a little bit. Okay, so the integral of e, that's just e times x minus e squared times x squared over 2 plus e to the third times x to the third over 3 minus e to the fourth times x to the fourth over 4. Okay. So you can see we can really combine those numerators. So you have ex. If you wanted to, you can put it as ex, e times x to the first, minus e times x squared over 2, plus e times x to the third over 3, minus e times x to the fourth over 4, plus so forth, so on, and so on. Okay, so these are the first four non-zero terms, which ends up equaling the sum from n equals 1 to infinity of -1 to the n plus 1 times e times x to the n over n. But technically, this would have been your answer.
Sum of -1 to the n plus 1?
Yep, the n plus 1.
That's just really light.
Oh, sorry about that. I think it must be reflect. There we go.
Okay.
Yeah, in some positions, I think the light just hits it a little bit wrong. I know I put a little bit of oomph on it. All right, so any questions on this one? All right. Anyone's? Anyone still writing? Looks like everyone's done. Let's see, I'll do this example. This one, again, find another interval of conversion.
No, I'll move it down.
Oh, yeah, that might help. Find the interval of conversion for the power series. The sum from n equals 1 to infinity of -1 to the n plus 1, x to the 2n plus 1 over 2n plus 1. Okay. So if we use the ratio test, we would see, so by the ratio test, you see that -1 from n equals 1 to infinity of -1 to the n plus 1 times x to the 2n plus 1 over 2n plus 1 converges absolutely for the interval -1 to 1. Okay. So we did that before, that's why we're kind of skipping that step now. So just like before, we just have to check the endpoints. Okay. Now for x equals -1, you have the sum of -1 to the n plus 1 times -1 to the 2n plus 1 over 2n plus 1. Okay, so this is just -1 to the 2n. 1 to the n plus 1. We're going to separate this as negative 1 to the 2n times negative 1 over 2n plus 1. Okay. Once again, this is just going to be negative 1 to an even power, so that's always just going to end up being 1. So we're going to add this negative 1 here. So that gives us the sum from n equals 1 to infinity of negative 1 to the n plus 2 times 1 over 2n plus 1. Okay. So we can check for convergence using the alternating series test again, since we have our negative 1 oscillating. So by the alternating series test, bless you. First, we have to find the limit of our a sub n as n approaches infinity. So that's the limit of 1 over 2n plus 1, which equals 0, so it passes the first test. And second, our a sub n plus 1 has to be less than or equal to a sub n, which means 1 over 2 times n plus 1 has to be less than or equal to 1 over 2n plus 1. So that's 1 over 2n plus 3. It's less than or equal to 1 over 2n plus 1, which is true. Okay. So both conditions are met, which means it converges at x equals negative 1. Okay, so we know for that negative 1, our brackets are coming. Now for x equals 1, we have the sum from n equals 1 to infinity of negative 1 n plus 1 over 1 to the 2n plus 1 power over 2n plus 1. Okay, so we know 1 to the any power is just going to be 1. So we kind of separate that a little bit. So we have our sum of negative 1 to the n plus 1 of 1 over 2n plus 1. And really, we can use the alternating series test again because we still have it oscillating. Using alternating series test again, because you have the exact same thing except the n plus 2 and n plus 1, but that doesn't really matter. So we know it's going to converge here because it's the exact same test. So it converges also at x equals 1. Okay, so that means your interval of convergence is from negative 1 to 1, but now we have a bracket on both sides. So any questions on that one? Now the thing is, for some reason with the book, their explanation goes way off into left field. I have no idea what they're even trying to explain. This is just a much easier approach.
That's nice of them.
Yeah. I was looking at it like, why did they even do that? They're going like way over here just to end up right back here. So.
Well, they didn't use the alternating series test?
Nope, they didn't. What they did was they went here and they found out that that was the natural log of something, 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 and then you find the derivative of that, and that gave you this, and then you find, I guess that's just way too much. That was just way too much work. So. Yeah, I think so. So. I don't know. For some reason, like I said, it just didn't make sense. This is just a whole lot faster and give you the same answer. Now, if their way would have been faster, I have absolutely no problem learning a new, faster way, but just so happens their way was not faster. All right. Alright, so we're done with the power series. Now we're going to go into the Taylor and Maclaurin series. I know somebody's thinking, how many of them are there? So we're going to stop with Taylor and Maclaurin. So we're not going to add any more series to it.
The last two?
Well, the last series, so we're still going to kind of mess around with those two, but these are the last two. So we have the definition of a Taylor series. Okay, so the Taylor series, the sum from n equals 0 to infinity of the nth derivative of some c divided by n factorial of x minus c to the nth power. Okay, so if we plug in our n equals 0, we'll have f of c plus f prime of c over 1 factorial times x minus c to the first power plus f double prime of c over 2 factorial times x minus c squared plus the third derivative at c over 3 factorial times x minus 3 to the third, and it keeps on going. And this is your Taylor series.
So when you run out of something to derive? What happens when you run out of something to derive?
Oh, then they'll just stop you. Well, you'll stop because you'll have no choice, but eventually when you keep deriving, it'll just become 0 over and over. So you can keep on going forever, but you'll just be adding zeros every turn.
But some things don't always just end.
Oh yeah, if you get something like sine and cosine, then they'll just rotate over and over again. So this is called your Taylor series. For f of x at c.
I think on the last one that you put x minus 3 to the third, not x minus c.
Oh, x minus c, thank you.
Couldn't tell because you're running out of room.
I know, I was trying to squeeze it in there. I think I was more concerned with getting everything in there than I was in making sure the c and the 3 wasn't switched up. Yes?
So that was the derivative of the f of c.
Yep, no, this is just the function of c. So if you plug in your c.
Okay. So every sum we have to find the derivative of c.
Yep, so here you just start off with your f of c. And then you have the first derivative of c, where x minus c is raised to the first. Then you have f prime of c, well, yeah, f double prime of c over 2 factorial. So really you're just going to have 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, and it keeps on going like that. So you have the fourth derivative over 4 factorial and x minus c to the fourth power. Then it keeps going and going and going. All right, so let's say if we let c equals 0. Okay, so for all of these, c is just equal to 0. So you have the sum from n equals 0 to infinity of the nth derivative of 0 over n factorial. And instead of x minus c to the n, it's just x to the nth power. That's going to equal f of 0 plus f prime of 0, x, plus f double prime of 0 over 2 factorial times x squared, plus the third derivative, 0 over 3 factorial times x to the third, plus, and so forth, and so on and so on. This is called your Maclaurin series. That's really the only difference.
So Maclaurin series is just a Taylor series at 0?
Yep.
Or c is at 0?
Yep, that's it.
Why even make a whole new series up?
I don't know, somewhere probably a couple thousand years ago, someone was like, I'll put a 0 there and my name will live on forever. So, I don't know.
Wasn't there something else like that recently?
Mm.
Where it was just, I think it was with P-Series. It did specifically a 0, it's something else.
Go ahead.
That was just the converting.
Series.
Oh, we keep saying series.
Ah, that's it, yeah.
It was P-Series and
That was funny. I didn't even expect that one.
Yeah, I'm surprised it took that long.
I know, we were yelling
Yeah.
series like
How many
crazy.
people got iPhone here because it's series 30 times?
I hate that.
I don't even know what it
Right.
is.
So C equals 0.
Right.
Google is-
This series is, well, becomes a McLaurin series.
I don't even know what I'm talking about.
That's literally just the only difference.
So if I just go to the board of mathematicians and say, well, when C equals 1, it's all of this. Can we have the Austin series?
Oh, harmonics.
Trust me, at some point, somebody spent like 20 pages proving all of this. Oh, you'd be surprised. The simplest things they will spend forever proving. I want to say the most recent one was, you know, you have x squared plus y squared equals z squared. They proved that those will work for a number larger than 2. I want to say this was done recently, like in
Wait,
in
what
the
are you
late
talking
90s.
about? Are you talking about the
Where-
Fermat's last theorem?
Yeah.
Was that? Yep, I think so. I think that's the name. I forgot the name of it.
If I recall, they
I wanna
proved
say it
that
was-
it didn't hold for anything above 2.
Was it they proved it? Well, it was either they proved it did or it didn't. I remember they spent 500 pages.
I forget.
Proving
what-
it.
I forget
It was
how many
one of them.
Required
pages it
some
was, but
really
isn't there,
out
like,
there math.
Yeah.
so many pages that it took to just prove that like 1 plus 1 equals 2 or something like that. And it
Yeah.
was just like this whole long like 15-page proof.
So,
This
yeah.
definitely is 1 plus 1
This
equals
is the
2.
axiom.
Like this is dumb.
Yeah, they will spend to be honest, they will spend years just
Actually, that
to
makes the
find
question.
something to attach their name to.
What's the shortest paper out there?
Oh, I don't know.
think it's less than a page. Like it's half a page or something.
What would it be on?
I want to say my thesis was
I don't know,
40
but
pages, so
It's so
that was-
weird.
was
Well,
horrible.
they'll spend so
That
many
was just
pages
horrible.
on one plus one, they'll have half a page for
it was on if you wanted to remove noise from two-dimensional MRI images using wavelet transforms.
Wow.
So it was
No idea what you just said.
6 months of my
What
life
transforms? Wave
that was rough.
Only 6 months?
Did you say Laplace transforms?
Oh, wavelet transforms.
Oh, okay.
All right, so let's say, for example, the series with the expansion, say e to the 42nd power plus e to the 42nd power times x minus 42 plus e to the 42nd power over 2 times x minus 42 squared plus e to the 42nd power over 6 times x minus 42 to the 3rd power. This is a Taylor series. Because it's in the right form. But if you have one that looks like this, let's say the sum from n equals 0 to infinity of e squared over n times x minus 2 to the nth power, that one's not a Taylor series. And the only reason is because it's over n and not n factorial. Since the denominator is n and not n factorial. So it's really, really detailed. Yes.
Is 2 factorial 2 or 3?
2. That would just be 2 times 1.
Oh, it's 2. I thought it was 2 plus or something.
Nope, it's just multiplying everything below it.
All right.
All right, so if we had, let's say, 1 plus x squared over 2 plus x to the third over 3, and so forth and so on and so on, then that would be your Maclaurin series. I swear it feels like it's like 10:30 at night.
Who does that?
Feels like it's been dark for an hour and a half. Just,
Well, it's 5:29. It was light all of 20 minutes ago.
With 6 inches on the grass outside.
I know.
Seen a lot of like clever things on Facebook and stuff having to do with the fact that it gets dark at like 4 o'clock. Like, hello darkness, my old friend. It's 4, wait, what is it? Why are you here? It's 4:30 p.m. or something like that. I forget what it is now.
I couldn't imagine living in Alaska where it's like 6 months of darkness.
Yeah.
Then 6 months of lightness.
I know, 3 in the morning, you're just sitting there in bed like,
Right.
so bright.
I know.
The inventors of the blackout curtain.
I know, that's the only thing you can do.
Right?
Blackout freaking house.
Oh, yeah. Oh, yes.
No windows.
Why was the
in
last
there.
series in McLaurin series?
Oh, because it was in the form for Maclaurin series. So you had here, if you had, let's say, x equals 0. Oh, let's say your f of x was equal to x. That would be x to the 0 power would be x squared.
Right.
I mean, 1. You have x to the first power would be x. You have x squared over 2 factorial.
Well,
Oh, actually, that
That's
should be
what I'm saying,
6.
yeah,
Yeah.
okay.
That should have been, well, actually, it should have been 3 factorial, which is just 6.
Right.
Yeah, that was it. Thank you. Was that what you were going to point out? Yeah.
Yeah, that confused me. All right.
All right. Okay, so let's say, for example, might as well restart.